getting red now?
Yeah.
Wait. What? Oh, yeah.
Yeah. Now recording started. Okay. Thank you, Arto.
So some practicalities at first. So we are recording this, and all presentation will be shared on our website after this webinar. And if you have questions, you can open your microphone. Otherwise, keep it muted, and we can also save this. Internet speed if we are not utilizing this camera connection all the time on. And then brief introduction about the agenda. As Teppo told, we have very interesting presentations at this moment. We started a couple of years ago preparing a European level project, and Jerker Delsing, he is the head of this Arrowhead FPN project, and he will introduce the project to all of us. That is something where many different European countries are participating, and we will hear more from Jerker. And after that, Leo van Ruiven from Netherlands give some example how to manage information exchange in a nuclear facility project. And after that, we will get a presentation from David Cameron from Oslo University about system approach to asset design interoperability. And then we are having some about 10 minutes break, and after that we are having presentation regarding PID diagrams and DEXP. Matti Huhtinen from AFRI and Gerardo Santillan from Semantum are giving the presentation, and later in the afternoon Miikka Tammi from AFRI is giving a presentation about dependability, model-based reliability analysis, and the last presentation will be given by Michael Meyer from Enershauser about integrated engineering. The topics is the same, how to exchange information between companies during investment projects or operating in a maintenance phase. And then we are closing around 4:30. I guess most of you have heard about THTH. We have two different divisions. I'm not opening that much, but I will give a few words about this KDT project. We are having all THTH members involved in this project here in Finland, and the Finnish part is part of the larger process industry applications where Sweden and Norway is involved, and that is part of this KDT project. But we will hear more about that, and I think that this is all from me at this moment. So maybe we could start the original agenda. Jerker, are you ready to give your presentation?
Yes, I am.
Very good, very good. Stage is yours.
Fine, thanks a lot. Thank you for inviting me, and we have squeezed this in. I'm actually at an island in a lake in southwest of Austria right now. But internet is working everywhere on this globe almost, so I'm happy to be here, and thank you for inviting me. And I will try to share my presentation, and I hope that everything will work accordingly, since I just need to click one specific button here. So bear with me a little bit, and we should be up and running. I hope you see
yes,
a headline.
Yeah, very good.
Very good. So Arrowhead FPVN, Flexible Production Value Network, is a European project funded by the KDT Joint Undertaking Schema in Brussels. KDT means Key Digital Technologies, and it's, as just an overview, it's a 30 million euro budget project. There are 43 partners, 12 countries, and the map is from still reflecting the countries involved when we submitted this. But now Poland has left due to non-national funding, and Germany is only one left, but it's an important player. It's Siemens.
Jerker, sorry to interrupt. Could you perhaps close your camera because of the internet connection? Some people are having difficulties hearing you. So, and maybe Arto, you could do the same.
Okay, I will.
I can do so. Let me. Okay, so we're covering 4 different application domains. One is automotive, one is aerospace, one is green energy and service, and the final one is process industry, production, paper and pulp, and so on, which is, for example, very important in Finland, with Stora Enso as one of the large end users involved here.
Jerker, you are muted.
Jerker, you are muted.
Can you hear me now?
Yes, now.
Yeah. This is the beauty of these online meetings. So the vision of Arrowhead FPVN is to move towards a really doubling of the European industrial productivity, thanks to that we can have machines that autonomously can understand what other machines are saying without having been kind of programmed to do so from the beginning. And this area is where we spend an awful amount of money to fix all this communication every day, and some people or number of data indicates that whatever budget for an installation of something new or changing something where we need to update software in particular, about 60 to 80% of the cost is actually to fix the communication and having the machines, enabling the machines to understand each other. And the 20 to 40% is just delivering the value, but taking away those 60 to 80% of the costs is the ambition here. And this will fuel the productivity very clearly. THT is a typical example of this. SEA is another. DexBiz is yet another association that are trying to support this direction. So we are very happy for your work in moving this, and this has probably also enabled us to get the funding for this project. So what is a production value network? This is a try to bring up this 3-dimensional thing and just making it very clear that it's 3-dimensional. It includes multi-stage stakeholder operation, owners, operators, engineers, engineering and procurement and consultancy and the supply chain and customers. And it holds a huge number of information at all levels here. And it's very clear that this information is kind of implemented in our OT systems using non-standardized models, using standardized models, and these models are also changed over time. And all this information exchange is necessary to get this to improve the productivity in this type of kind of complex industrial domains. It's not only within the factory, but it's within the factory plus the supply chain, both upstream and downstream. So what is the grand challenge that we have taken on in this project? As I kind of indicated, there are too many non-interoperable data models. And as a matter of fact, many of these data models, they are standardized. But they're standardized in their domain, in their silo, without thinking to how to work with others. Within this project, we are looking into actually changing this. How can we get more interoperable data models? And the other gap we also see is that technologies for translating different data models to other data models is really non-mature. Things has happened since we wrote this proposal, and in particular, the world is facing technologies like ChatGPT, and this was already foreseen that we will work with these type of technologies, but we might have got new tools since we wrote the proposal and until we now are starting the project in the 1st of June this year. And it's since we are working across various domains and where people have different architectures, different technologies, different implementations, different suppliers, there is also a lack of open architectures and implementation platforms to support this type of interoperability. And where these platforms, for obvious reasons, need to be flexible, changing with time, they need to be secure, they need to be scalable, and they need to have capabilities to support this autonomous translation of data models. And we have selected 3 enablers to do this. This is working with microservice technology. This is very popular in the cloud domain, but we are now trying to move this to the edge and very far edge in our automation and operational technology work. We will work with a limited number of major digital data models, standardized data models, and we will target to have the capability of autonomously translate between these data models once the machines actually discover that's needed. So the whole project stands on 3 pillars. We're talking about the microservice paradigm to enable this. We are talking about a number of major industrial data models, standardized, and there's automated translation between these data and information models. What is the baseline? Where are we starting? We are starting on results that really comes from a project named Arrow Tools that ended last year, and I was coordinating that one as well, and we achieved some quite interesting results, in particular to reduce engineering cost for building automation solutions in the world of production. This builds on a set of projects that has been around since early 2000, and where we have developed and created what is now called the Eclipse Arrowhead open source technology. And what is the target for this technology? It's actually to integrate our operational technology with all the new stuff in the IT world. 5G, cloud, IoT, system assistance, big data, blockchains, AI, etc. So it's very much enabling us to still keep the old existing OT stuff, but enable the efficient, engineering efficient, cost efficient, time efficient way of integrating these two words. And the particular focus of this project is to look at the data models and how can we simplify the translation between those. And this has so far been the major bottleneck in this creating the autonomous interoperability in the automation digitization domain. So the Arrowhead Tools project was targeting 20 to 50% reduction of engineering cost in automation, and I will try to tell you what happened. So
the Arrowhead Tools project set out to build a tool that could substantially reduce engineering costs and time for digitalization and automation solutions. And we have succeeded to show exceptional savings of 30 to 95%. This is verified and validated by more than 25 industrial use cases from semiconductor, automotive, mining, buildings, logistics, maintenance, and smart cities. Concrete realization in the industry is now supported by the commercial ecosystem of over 20 European companies. So how did we succeed? Our technology is provided open source as Eclipse Arrowhead. It's free to use and consists of more than 25 basic building blocks and engineering procedures and tools, providing out-of-the-box security, flexibility, and scalability, enabling efficient solution integration supported by established training and support channels. The released technology is IPR checked by Eclipse Foundation. Our continuous mission is to further simplify usage and improve robustness. So let's come together to accelerate the journey toward a more digital and greener future. Eclipse Arrowhead, powering Industry 4.0 and beyond.
It's quite interesting. I just half an hour ago made a presentation to yet another European project called AIMS 5.0, which is led by Infineon. And one of the guys from Infineon who participated in the Arrowhead Tools project, he previously said that they've saved 80% of their cost and time in adding new machines and sensors into their semiconductor production. And today he said, no, it's even more. And so people are using this in industry today. And so I wouldn't say it's an omnipresent industry or technology, but it's very much explored and really tested, and there are benefits. So this is the baseline where we start with the Arrowhead Flexible Production Value Network. We have the foundation for how to build these type of integration from OT to IT, but we're now trying to see, can we take away the bottleneck of the data models as well, which still is a huge huge bottleneck. So we have the microservice paradigm, and it's very much about modularization of software and to define microservices. And the starting point is the Eclipse Arrowhead architecture and its reference implementation. We need capabilities of discovering which services that's around and what language they talk, which are the data models. We need capabilities of orchestrating who should talk to who, and then we can find that out. And we also, of course, need the security parts. One thing is interoperability. It's not only data models, but it's also protocols and all these kind of things. And translators for this and adapters for different type of protocols, that's already existing and is provided by the Eclipse Arrowhead framework. These things can be used, but now we want to extend these translators with the capability of translating the data models as well. So there exists a lot of these interoperability protocols, and there also exist some of these data model adapters. So for example, ISO 10303 has an adapter into Eclipse Arrowhead already to enable translation to some other languages. But in general, let me discuss what is the problem with data interoperability. It's a very complex thing. So there is a number of these big standards, and they are defined, but they are also being redefined. So for example, right now, there is a work of redefining 15926, led primarily by the Norwegian oil industry and others. And they are here in our project. And we want to enable these data models to be interoperable. And the thinking is, one of the things is here is to go over what's called the semantic web technologies, which is also a standardized approach to how to describe data. So can we then propose how future updates of these standardized data models should look like? I think that's a good help in reducing the cost around the non-interoperability between data models. Just to give you an example, how hard it can be. This is from two different sensor technologies, two cyber physical systems who are sending a message. And this is how the data model is interpreted using the ML standard. CPS-A and CPS-B. Do they look similar? A little bit. Both are talking about temperature. One is talking probably Celsius. The other one is probably talking Kelvin, so on. It's very clear. It's based on the same ontology, same standard. It's the same data, but they don't look the same. And why? These have been programmed by two different people. And this is what we very often see. Even if we have standards, they are not even implemented correctly, or the specifications are not tight enough to enable implementation, which means that two machines will actually understand each other. Since in this case, a reader or a consumer of the CPS-A and the CPS-B, they will probably say, no, this is not the same thing. Giving that they have one type of code to read it. So this is a typical example of the data model or non-interoperability thing that's around. And this is costing money to all of us. We have defined three approaches to look at this. One is to look at what we call super ontologies. The other one is using machine learning AI, and the third one is model-based, and I will detail a little bit on what we are thinking about. So this is the AI stuff. Can we, based on data, train this translator, TAB here in the middle, to work with us? And this is work that has been carried out over the last couple of years, and this is just explaining what are we after. This is the translator that we would like to train. And yes, we can do this for example, this example I gave a few seconds ago. So here we start to have some reasonable results. And here we are very close to using things like what ChatGPT is trying to do as well. And we can skip that one. The other one is to build what we call super ontologies. If we know what a producer has for such data model and what ontology or standard they are using, and then we know what a consumer can understand, can we then build kind of a super model, super data model, where we can make the translation, so kind of a more or less hard-coded translation, but with the help of the super ontology thing. And this is an approach that, in particular, some good friends in Portugal has been quite successful. So there is already existing technology where we have tried this, so there is good possibilities that we can succeed in refining this. And the third thing is about model-based, and where we can then use computer science approaches regarding what's called declarative technologies to declare the results out of what we are coding. And this is very often used through modeling languages like UML, SysML, and other declarative languages. And this enables us to automate code generation that will actually then provide new code to the consumer that it can actually understand what the producer is providing. So this also indicates that we can support the engineering of this, so we don't need to find that code having it to be developed in a lab and then being deployed, but that the machines actually can do this themselves. And there are work that actually indicates how this can be done, that we can introduce a new interface between a provider and a consumer, enabling the consumer to understand what the provider is saying without any human intervention. So we expect some impact out of this, that we can integrate these things and that, for example, asset information models can be translated into other languages, other standards, and that if we are bringing in new technology functionalities, having new data models and so on, that these can still be understood by the existing legacy technology in there. And then it's also clear, how do we transform our operations into actually using these technologies? So the change management, so improved digital transformation management. This is yet another impact that we see, and where we will work concretely to test how this can be done. And finally, we will test all this in a set of use cases in the automotive domain, in the first two ones is automotive domain. The next one is oops, now I'm missing which domain that is. The third, yeah, it's the aircraft. It's the aircrafts or avionics domain. Then we have the energy, and then we have the process industry, and the last three ones. So we will test this in all these use cases and see whether we can validate that and where we can change these technologies and really achieve the impact that we're looking forward to. So in conclusion, the ambition is that the machines can autonomously translate between major standardized data models. Yes, we haven't started yet. We're going to start on June 1st, and we will have a kickoff in Helsinki on June 13, 14. So I guess I will see some of you there. And it's also clear that we will have a close collaboration with another large European project, AIMS 5.0, led by Infineon, and that's where I am right now at their kickoff. So I hope this was a brief introduction of an understandable introduction, although I don't have the possibility to join you face to face for this THT event today. So any comments or questions are highly welcome. Thanks for listening.
Thank you very much, Jerker. Do we have any questions at this moment? I have at least one question, or maybe I could also ask that from myself, because we have been preparing and we are part of these process industry pilots, this 3.9 on your lists, what we saw, and we are preparing our issues, and I was wondering, how do you think, how much we could get these tools used in the pilots, or do you think that what would be the biggest obstacle in order to get them piloted in a proper way? Do you have any ideas for that?
For these pilot use cases, I'm pretty sure that we will be able to test these tools and technologies clearly within the 3 years of the project. So that I don't see any big hurdles. It's more that we really have the ambition to work together and try things out. Yeah, I've done this a few times before in others. So yes, what we develop as these core technologies can be tested and very often have been, and I'm pretty sure that it will be in Arrowhead Flexible Production Value Network as well. The larger obstacle is how can we then spread this to a more widespread usage in the industry. This will probably require a little bit of tweaking of how industry is organized and so on. So this is why we also have concrete work on this digital transformation capabilities and more also providing, here is a kind of a roadmap for how you can roll this out in big companies like, for example, Stora Enso, because they are clearly interested in looking at these things, as far as I understand.
Yeah, that's right. Okay, that is really big challenge to get this all these information disseminated to all parties and get them familiar with these technologies, and that is one part of the project what we have doing in our own internal project in THTH. So this is supposed to support all this dissemination idea.
Yep. Here, THTH and SEA, for example, and POSC, CSER, and XP are very important organizations to say, okay, we start to understand and we can use our networks to further spread the word that there is money to gain, thinking in a little bit new directions.
Yeah, very good. Okay. Do we have any other questions to Jerker or comments? If not, thanks a lot, Jerker, and have a nice meeting there with Infineon. We will continue the next presentation. Then Leo van Ruiven from Netherlands. Leo, are you ready to give your presentation?
Yes, I think so.
Okay, very good. So take the stage for you.
Yes. Well, welcome. This is about a project for nuclear facility, about cores for data integration, and lifecycle support use case, in fact, for a nuclear facility based on 15926 part 11. I myself, I'm already 20 years and in fact the chair and member of the Dutch Standardization Committee, Information Integration Interoperability, member of ISO 18464 Industrial Data. I'm initiator and editor of 15926 part 11. I'm already 20 years involved in as EC member of the USPI, and I'm initiator and architect of the PALAS alphanumeric part of this common data environment, the PALAS ontology, and the project RDL for PALAS project. In fact, what I will show the next half hour is just some context of the project, challenges of information management, the structure of the CDE, the positioning in the project, and a recap of PALAS concept. The project itself, PALAS is preparing the replacement of aging high flux reactor producing medical isotopes at location Petten in the Netherlands. It's one of the 6 reactors in the world produces isotopes, especially for cancer research. It's now, in fact, the end of life, and before 2030, we have to up and running a new facility. It will look like this. This is the representation of the 3D model, in fact. So it's quite bigger. In fact, it's 1.5 billion euro project. So it's quite a big project, in fact. And the mission of PALAS is to arrive at a data-driven production, isotope production, and data-driven asset management. Since it's quite a critical logistic process to produce isotopes and to distribute them worldwide. So that really needs a data-driven approach. And it is also a facility that has to be operated during 50, maybe even 60 years. So also asset management should, in fact, a data-driven approach. The foundation of the meaning is to be able to arrive to the data-driven approaches, that information management and configuration management are key at the very start of the design of the project. Assuring reliability, safety, and especially because it's a nuclear facility, it's about the license to operate. We have to prove to the authority in the Netherlands that we have full control over all changes and fulfilling the requirements. But also supporting sustainability ambitions and regulations, controlling changes, optimizing CAPEX and OPEX. And also we use knowledge and creation of the learning capability of the organization during the existence of this facility. But we have a challenge, and we know that companies, engineering companies, but also each company in general, have really problems to implementing a sound information and configuration management for mainly two reasons. We see that the design is really fragmented across time and fragmented across disciplines, and is based on tools, engineering tools from different vendors, lacking interoperability. The second thing is that we see there's a lack of integration of domain knowledge, information modeling knowledge, and IT knowledge. These are three very important pillars to do this kind of information management projects. Going to the fragmentation over disciplines, this is just not specifically for our project, but in general, we see that we have, and we're talking about, in fact, about one-offs projects, which are designed and built in a combination of parties, which by coincidence, in fact, are working together. And all those parties has their own design and construct process and uses their own tooling. And hopefully in more or less extent, those design and construct processes are based on systems engineering, like the ISO 15288 standard for systems engineering, but they all implement systems engineering in a slightly different way. They all have different maturity on really doing it. So what is left is just that you take account of exchanging and sharing information so that every party can do his job efficiently, effectively, and so that every party gets the information with the right quality, on time, complete, and also is able to put the information that he produces back into the circle. And for this project, we have chosen to do that exchange on open standards. An alternative could be that you choose for just one big vendor solution, but then you have a vendor lock-in, in fact. and you don't know what's happening over 10, 20 years. So that's why we have chosen for open standards for communication between those parties. The other challenge is the fragmentation over time. We have the world, say, as required, the world that defines the requirements, what is there to be there, inclusive its behavior. We have the world of design and realization, which which makes the how of the facility, and we have the as is, the as built situation of the plant. And the challenge is to prove and to show that those three worlds are mutually compliant with each other, which also take into account the changes in time that are as well on design level, engineering level, as later on the plant on asset level. In fact, this is what we call the equilibrium triangle from the nuclear energy atomic agency. And those three worlds are separated, in fact, by three main reasons, because the three worlds are organizational different, use other technologies, and has other uses another language semantically. Those are the three, according to ISO 11354, which is, by the way, a very good standard on interoperability barriers. And the solution we have chosen is to arrive to a common data environment based on ISO 19650 and BIM standard. It's a process standard how to deal with this. And it is based on a reference data library, or say an ontology based on 1596. Using this way, we clean the data and integrate the data from those three worlds into a common data environment. So it becomes really one environment that represents all three worlds in a consistent way. The background of the common data environment is formed by structures, breakdown structures. You need a structure to relate all the data to. And we have recognized 8 main structures, like the document breakdown, the requirement breakdown, system breakdown, etc., which forms, again, the basis of the common data environment. This is also in line with the ISC 81346 standard. Secondly, we make relationships between the elements of those structures by semantic relationships, and giving the elements, we characterize the elements by giving properties to them. The relationships are defined in the ISO 15926 part 11, which together we created for this project an integrated information model. And every element is classified according to the reference data library we specifically create for this project, since there is no reference data library that fits all. So we make a reference data library and we compose it from other libraries like the 1596 part 4, IFC, Uniclass, ATIM. We create a reference data library that's appropriate for this project. Then we connect the documents. We still have a document management system, and we connect the documents to the elements. We have the 3D model, which is fully IFC based. This all parties delivers their 3D models according to IFC standard, and we integrate those 3D models into one. And we connect the 3D objects with the system breakdown and the geographical breakdown structure elements. And we have the schedule and cost model for the 4D planning connected to the work breakdown structure and also to the geographical breakdown and system breakdown. We also apply a lifecycle model, which in fact a lifecycle model on equipment level, at least according to 1596 part 11 and the European 17632, a new BIM standard, which recognizes that we have the planned functional entities, like the symbols on the P&ID, in fact, which are implemented by technical plant entities represented by the 3D objects. Well, and like in this case, the centrifugal pump is implemented by a specific horizontal centrifugal pump with specifications in that sense that it can be bought in the market and like a manufacturer and model and serial, of course. And it starts to perform at the end and hopefully according to whatever was required on the functional level. So we have 4 quadrants, which the quadrant 1, 2, and 3 has their own identification, their own identity. So there are separate entities. So we can manage the data on each quadrant separately in the common data environment. So we can say that in fact, with a shortcut relation, that a specific pump is fulfilling, is installed as the functional thing on the P&ID. But that also, if the pump is replaced, we recognize that the second pump is also installed on the same place, a functional location. So you can trace back which equipment ever has been installed on that place, on that functional place, and also how that specific pump has performed at that time. So that makes it interesting indeed to start capturing data via IoT, SCADA, or management systems, and to do analytics on the performance and to check if it really is whatever was required. And if not, what has to be changed or corrected, the installed asset or the technical design or even the functional design or the requirements. So you can make explicit the difference between those 3 entities. In fact, this should be the fundamental ingredients for a full digital twin, which Pallas also is aiming for. And then the interesting problem we have with information management, the controlling of information input and output of the engineering processes, knowing that we have the various disciplines like civil, mechanical, electrical, instruments, and maintenance with their own tooling, 3D modeling tooling like Revit, SolidWorks, P&ID tooling like Bentley, Aviva, etc. How can we get a neutral and consistent representation of all the design of these disciplines? Now, that's how we do it, is that based on the information model and the reference data library, we have a workflow getting data from those tools and cleaning and integrate those data streams into the common data environment. We need for that and we have introduced for that an information delivery team, which also is defined in the ISO 19650 standard, the BIM standard. And based on baselines, in fact, we can feed back the data to the disciplines, so they use data for the further development of their design. Is based on using the data from the common data environment and not their own database and their own spreadsheet. So, and then we are able to give an handover to the client as a common as a neutral set of representing the information of the design. So we recognize, in fact, the work in progress status is done in the tooling themselves. In the CDE, the common data environment has the status shared meaning sharing between the disciplines, and the status published as baselined and hand over to the client. The car wash is really represented by a car wash, and taking in account the data quality rules given in ISO 8000, taking the raw data sets from engineering tooling, and we start to check the right syntax and references like tag codes, room numbers, the document numbers, if they are correctly, and also if they really exist in the CD, if they should. Then we harmonize the semantics that we receive in the data sets. We harmonize with the integrated information model, and we classify all objects according to RDL. And we identify, since we regularly get new data sets from the tooling, we identify additions, changes, or deletions to register them and to make them traceable. And we apply the rules of the relationships. So we arrive at cleaned and signed data sets to import in CD. It's based on signed named graphs, because since it's a graph database application, you all work with named graphs to store all the data. And in fact, the same, this is for non-graphical data, but we do the same for cleaning the IFC 3D model we receive. We also need really a cleaning before we can integrate the 3D models with the non-graphical data. So we arrive at a kind of ecosystem, in fact, which giving the engineering processes over all disciplines, all contractors, over the whole life cycle. We get the export of legacy engineering tools. We clean them based on the integrated information model and reference data library. So we arrive to a cleaned and integrated data set, which can be seen as master data as input for any engineering process. And we have a view on CD based on we can do on Sparkle. We can do any extract of the CD and put it in either Excel, or we can present it in apps. And we have the baseline handover as a structured file. In fact, we use a reified trig as a format to hand over the information to the stakeholder, being in fact the client, which can start executing their business processes on the same consistent data. And they use the same IAM, integrated information model, and the same RDL. Small example, project data. For instance, we have a pump with a relationship to which is in a room, is a subject of an arrangement drawing, and the arrangement drawing has a relationship to a work package which produces that drawing. Then all the project entities has a relationship, an RDF type relation to, in this case, the planned functional physical object. The room is spatial location, the arrangement drawing is a document, and the work package is a activity. And then with this also the relationships are defined, including the range and domain and range of the relationship, and we can validate if it is correctly done. And we classify as secondly all the things, like the pump is classified as according to the RDL, vertical centrifugal pump. The room is classified as an engine room, and the arrangement drawing is a general arrangement drawing, and the work package is a work package. So there are two components: the relationship to project data to the integral information model, and a relationship to the RDL. And the combination makes it really that the all project data is explicitly defined, can be validated, and is traceable. This is how it looks like in the graph database. It's exactly the same picture as this. And this is how it really looks like in the graph database. The point is that it is really human readable. You can really, as a human, read the data in the graph database, but it is also computer interpreted. And that's, in fact, a strong point, especially in this moment in time that we have still difficult to explain and to learn people how to use it. If the data can be really read by human, but also can be processed by computers. We use baselines. Baselines is the whole configuration management is based on baselines. And we define baselines on the graph, the signed named graphs. And at a certain moment, you can say you can introduce a new baseline, which in fact aggregates the previous baseline and starts to collect new incremental uploads. So you at any time you can ask what the original baseline is and what the actual baseline is and the difference between them. Recap, what we see is on the information point of view, you have to select and tailor data standards and develop really an iterative and information model and RDL appropriate for your project. And you can reuse, of course, existing information models. And focus on information streams you detect in the project. Information streams between the information management system, between disciplines, and agree on exchange requirements with engineering disciplines and the IM environment, and apply the principle ISO 8000. So we recognize syntactic, semantic, and pragmatic data quality. We also see that data quality anyway is gaining more and more also legal significance when it especially in projects. The technology, I think the only way to do this is using semantic modeling technology. You can't do this anymore with traditional database technology like SQL databases. That's not doable in this rich environment of systems engineering data. The amount of tables you need is far too big to handle that. And we have, by limiting ourselves, only use RDFS. So we don't use OWL or Shekel or whatever. We only use really pure RDFS. That's the reason, I think, why we are succeeding in this, because it keeps it stupid simple. And that combined with Sparkle and named graph is a very strong mechanism. And we have the human organization. We need a clear vision, and support of senior management is really crucial that you have that. We need new competences, and we have to bridge the gap between the theoretical ontologies, engineering environment, and engineering tooling. And we have to organize the integration between domain knowledge, semantic modeling knowledge, and IT. You have to integrate and to organize these knowledge fields. And as last slide, we have looked at what should be the adoption. Can you adopt this concept in other projects? Well, it's not a one-fits-all solution what we do, but it can be tailored and scaled. But you have to take into account these general problems we have and see in projects. You have to recognize that partners in the project concept has their own methods, standards, and tools, and they will keep using them. They have a different maturity, thinking data quality and data modeling skills. Contracts in many cases don't take explicit account data quality and data exchange procedures. The vision and support of senior management, project management is crucial for what you can ever achieve in a project. IT platforms and software supporting real data integration are still in development. You have to recognize that. And in general, within companies, there is a lack of knowledge of data integration standards. We see in the Netherlands anyway. And we see that the gap between ontologies and knowledge of it in regular industry is really huge. We forget that frequently. We forget that people familiar with ontologies, talking about ontologies, at a certain moment it becomes quite easy for them, but realize that in the companies, it is really not known there, and there's a real big gap that makes it quite difficult to introduce this kind of work methods. Yeah, that was really in a nutshell, because you must realize that this is normally we take some more time for this. It is quite a big story, in fact, to tell in this time, but I hope it gives some ideas what we are facing.
Yes, for sure. That was very impressive presentation. Thanks a lot. Have you any questions to Leo? I have a few questions. The first one was related to this last slide what you had, and especially this you mentioned this senior management visions and support what is needed here in this type of projects, and was that evident that you got that, you knew that in advance that you will get that support, and those senior management people, they are really aware of the solutions that helped you, or
Yeah.
or
Yeah, sure. That should, if we didn't had that support from the beginning, I think it would be impossible to achieve what we now have achieved. So what I till now see that projects where this kind of approaches are successfully, it always has to do with mostly by coincidence, the right people with the right minds has been brought together, including the management, is really crucial as a success factor. Say, because if you don't have that support and you start from down under, it's since it takes time, it takes money, and it's always difficult. It's difficult subject, difficult matter. So if you don't have management that has the vision of doing this and have at least some feeling about the matter, then it's really tough to explain to them why you should pay money to this and time to this.
Yeah, that is sure. That is a subject we have been discussing constantly in our community, how to get that kind of vision and support from senior management. That is a tough thing.
Yes, yes.
But I have one additional question. This is an environment where you are applying tight regulations, and does this tight regulation bring additional challenges for the work, or was that?
Well, in fact, in this case, it makes it some easier.
Okay.
Because you can refer to the fact for the license to operate. We know, because it's a nuclear facility, we know we have to the authorities to prove that we control the information and especially control the changes. So that makes, in this case, it made it a lot easier to explain why we need this approach and why we need this kind of information management, especially configuration management mechanism.
Yeah, okay, that's very very interesting. Is there any questions now to Leo? If not, thanks a lot, Leo.
All right.
And,
Yes.
And the next presentation is coming from David Cameron from Oslo University. David, are you on the line?
Yes, I am. I'll just try to share my
screen. Yeah.
My window. So can you put it into slideshow mode? Can you now see the slides?
Yes, it looks fine.
Okay. Well, thank you, Arto, for inviting me to do this talk. My name is David Cameron, work at the Centre for Data Science at the University of Oslo, but actually have a long history as a chemical engineer. Worked in the industry and then in the simulation industry, but the last 8 years I've been at the University of Oslo working on trying to link informatics to the oil and gas industry. So what I'd like to talk today is summarize some work which has been done particularly in the Norwegian oil and gas industry around looking at systems approach to asset design interoperability. And the financing and testing of this work has been greatly benefited by a field development in the North Sea, which was originally 2 operating companies and 2 EPC contractors, Equinor and Ibel working on part of a large interlinked field, and Aker BP and Aker Solutions. And the field used to be called Noaka, north of Alvheim, Krafla and Asja. But as often happens in the oil and gas industry, people sold rights and transferred operating rights. So what is now happening is that Equinor has transferred their operatorship to Aker BP, and Ibel is still doing the bits of a field that Equinor was originally doing, and Aker Solution is doing the bits of a field that Aker BP was originally doing. And the field has changed name to Yggdrasil, which is a challenge for pronunciation to English speakers, and is a reference to old Nordic mythology. But what we are doing in this project, and what this project devoted resources to try out Industry 4.0 and try out how you could achieve digital data transfer between the operating companies, the EPC contractors, in this coordinated interlinked development. And so resources have been devoted to prototyping and testing out the standards that are available for data transfer. Now, what we discovered very early in this process was that when people started talking about interoperability, we found out that there were a lot of terms and thoughts and ideas which mean about 14, 15 different things each. So I just want to start my talk by pointing out that we have to be very careful, because words like product, function, process, stream, system, and activity are incredibly ambiguous. And so we always have to ask, when talking to each other about operability, well, what does that actually mean? Let's go back up a level of meaning to try to understand what we're doing here. So, based on the work we've been doing, we have a message that I'd like to carry across today. And this is based on our experience of looking at the data interoperability of what we've been doing and looking at the standards that are available for what we do. And my statement is, okay, we have OK models for representing installed equipment and as built with a tag structure. And then the direct design data related to that, exactly as we saw in the last presentation. And the things that are the standards that support that are the BIM standards, 15926, GFOS and DEXB. What we, however, have lacked is models for systems thinking, top-down design, and what we would call an aspect-oriented digital twin. Now I'll come back and try to explain what that is by going on a bit on. And I'll also try to at least defend this statement. And it comes down to a question on what is a system? A system depends on what perspective you'd come from. So if you're coming from 1596 Part 2, Part 4, and I just checked in Part 11, or the basic foundational ontology view of a world, a system is an assembly of physical things. And every part of a system, I saw in the Part 11 document just now, that ports and interfaces are also physical things in a system. Now, ISO 81346, which is a system breakdown standard, seems to be a bit schizophrenic about that. Sometimes it's a conceptual idea, but a lot of time it's also an assembly of physical things. INCOSE and systems engineering has a much more abstract idea of a system, which is they view the system as being a way of analysing reality or a way of conceptualising a desired reality. Now, what I'm going to argue here is that we need to have a framework and ontologies which support both of these ways of thinking about systems and provide linkages between them. And what we see here is there's actually quite an old concept called aspect systems, which my first encounter with that is a book published in 2010 with Wolfgang Marquardt and his collaborators at the University of Aachen, talking about an ontology for chemical process engineering. And they defined up that you have a system can be looked at from different aspects. And what we see here is that when you look at a large chemical oil and gas facility, we have different aspects that respect different concerns. So here we have a rather digital looking process design engineer in a design construction phase. And her question is, what is the process we need to build? We've got a task of producing this certain amount of oil and gas over this time history. What things do we have to do to process that oil and gas? And then they interface down into the design process where the piping mechanical engineer then asks the questions, good, to realise this process, what is the equipment we need to do that? Once you're back across into operations, you again have the same sort of aspects. Your maintenance engineer is asking a question, how do we ensure the equipment is running as it should? Very related to that the equipment is meeting its equipment requirements. But then the process engineer is asking some questions about how the equipment's working, but her interest now is about optimization and troubleshooting the process. You know, how well is the process meeting its functional requirements to produce the right amount of oil, the right amount of gas, and make sure that all the water is removed and pumped back down into the well. So if we're doing modelling and information management, we need to capture these different aspects and different concerns. And I would also say that in operations, when we're analysing data, it is one of the major challenges I used to have as a person going in and trying to do troubleshooting studies for processes, was that you had to weed out and get access to the process information by wading through large amounts of equipment information and trying to integrate it again. And one thing we also see is that often a lot of the process decisions we've made, you lose the rationale and you lose the data because it's been all flattened down into large amounts of equipment data. So what I'm going to try to talk a bit about here is a way of separating these concerns, focusing on these aspects so that you can, we hope, have a better capture of information in early phase design and can also reuse that information to create operation support systems when you're in operation. Around this, one of the tools which was developed as part of this was a concept called the information framework, which allows us to apply systems engineering principles to our engineering information. And this was developed in a joint industry project which was closely linked to the NOACA field development called READY. And READY was originally about digitalising requirements. But quite early in the process, they discovered that it's no point digitalising requirements unless you have a clear statement of where that requirement actually applies. And so the project then looked at how do we identify and create objects that you can apply requirements to. So it's based on the approach of ISO IEC 81346, where you break systems down into subsystems along agreed aspect trees. And we saw those aspect trees in the previous presentation as well. And they're typed using a reference designation system. A RDS has been developed for oil and gas, but it's easily extendable to process energy industries. And it has this aspect approach that allows you to separate function from a physical object. And we hope it allows us to give us easier access to why questions in what we're doing. You can also incorporate an old tag-based or product-based approach into this product aspect. So what IMF does is follows the approach you see in ISO IEC 81346 and gives you a starting point, 3 breakdown trees that you use in your engineering. The first is a functional breakdown where you focus on what you want to do in the facility you're building. And you break that down and you can type that by ontologically by activities, by verbs. And then in what they call a product aspect, which is in some ways, I don't quite like the word because product is a very ambiguous word. Perhaps equipment aspect would have been a better term, which is talking about artifacts. And they're typed by ISO 1596, physical objects and artifacts, covering that. And then you have a third aspect of where is the thing you're doing, which is the location aspect. Now, as we saw in the previous presentation, 81346 allows you, and in fact, engineering design requires you to create other aspect breakdowns as well. And we'll come back a little bit to that. But this is the basic point of IMF. Now, 81346 just gives you a breakdown. IMF gives you an object structure behind each object in the breakdown so that you can associate parameters to those objects. So IMF is currently under development and it's being tried out as a way of structuring the process engineering information for transfer between IBLE and, in the first case, Equinor during the feed phase, and now between IBLE and Aker BP in the engineering phase. Related to that is that this sort of argument is also something that has been observed and developed in the German process industries, where the ENPRO project identified that a plant life cycle is separated into 4 aspects with underlying data structures. And when we're looking at functional requirements, we're actually looking at functional systems which give you a structure of things that you're doing, which you then take over and then say, well, what artifacts do I need to have to realize these functional requirements, which then goes into the next phase. And it's exactly from a functional design to plan specification to plant in operation is exactly the same box as was shown in the previous presentation around maintaining information along the life cycle for the functional artifacts. The difference in approach is that we have these functional systems which are not deliberately tied to pieces of equipment. They are functional requirements for an assembly of equipment that you're going to have to realize. So here's our conceptual model of an asset information system using these aspects with some life cycle. And what we say is that there is a system that we wish to build, and there's different aspect representations of that. When we start in design, we look at the functional aspect first, and then that functional aspect process model is then realized by a product aspect model, and then you have an installed breakdown as well. And then you have under that at various degrees of configuration change management, administrative information, project reference, visual presentation. One thing we are beginning to be aware of in IMF is that we're not quite sure whether everything should be put in graph databases or everything should be in RDF or everything should be ontologies. We see there's a certain need to have a graph defining a structure of the models and defining the parameters. But what we see in engineering, there is so much information that needs to refer to those data points, that you could achieve a great deal more scalability by trying to have some sort of hybrid implementation of objects with parameters typed by ontologies. So we can see this the same idea. You can apply that to the V model, where during conceptual design, you're building up a breakdown of functional systems that are giving you your process constraints, requirements, and constraints. And then as you move from process engineering to plant engineering and detailed design, you're then applying your equipment requirements and constraints to define the artifacts that will realize your design. Once you're back out in construction and operation and maintenance, you're going to be asking your plant model to give you the information you need to make sure that you're complying with your equipment requirements, and that's maintenance. And you'll be asking your process model to ask how well your operation is complying with the process design and rationale to provide operational support and optimization of the process. Now, what we see is that there's a gap in the standards. And that question came up in the DEXP project by asking, well, we wish to represent block flow diagrams and process flow diagrams. And so the question is, well, what does a symbol in a block flow diagram represent? It looks like a distillation column, or it looks like a pump. Well, yeah, but actually it's not a distillation column or a pump. It's actually a system that performs a pumping process, or a system that performs a distillation process. And the system, that system is always more than the column itself. It will always be the column with the associated functionality and equipment that needs to maintain that column safely operating. And so the initiative was put in DEXP to model BFDs and process flow diagrams. And we moved away from the original DXB way of doing things, which was having classes typed by type of equipment, and moved towards the aspect system approach as implemented by AutoCAPE, and defined up that you build these DXB plus PFDs, process flow diagrams and block flow diagram models, from system blocks. And system blocks have ports with different types and interfaces. You have flows of material, which we can call a stream, energy or information between these blocks. You can type the type of material that you're transmitting between the blocks by defining a template for it, which gives you the information that's in the stream table. And so that each material state being transferred between a system has a certain data structure related to that. And then we need all sorts of bookkeeping blocks like sources and sinks, which can function also as off-page, on-page connectors. And we model instrumentation using a set of instrumentation activities to build up this. And using this data structure, we have an ability to capture the system breakdown that we have in conceptual design of a process, and we have a one-to-one correspondence between these system objects and the graphical representations in PFD or block flow diagram. And we see these sort of things again from the NPRO project. What sort of things are we talking about at different stages of a heat exchanger? At the functional requirements stage, what you're looking at is a high-level definition of what you want to do. I want a pump. I can then simulate without a defined function. I want a pump. I want to separate. But then at functional design, you've got down to the level of saying, well, okay, I want a pump with a centrifugal pump, or I want to pump, or I want to separate using distillation. And at those stages, you're doing steady state simulation. And the documentation for these things is process specification sheets, process flow diagrams, and you're doing a lot of the conceptual work necessary to design your safety philosophy and isolation philosophy. Around realization, you're then doing work around piping and instrumentation diagram of the surroundings of the equipment. And between the process between functional design and equipment design is actually a process of saying, for this system, I'm now going to have to create this assembly of equipment that will fulfill all the primary functions and supporting functions for that particular functional system, that particular pump skid, that particular distillation column. So what we see building design, is that a lot of the early functional design, conceptual design, is built up by building a hierarchy of systems. And they're built up like those little dolls which fit into each other. In the interests of sanity and interface control, you define your system boundaries to be the natural places where systems start and end. And you build downwards from a field block diagram saying, I've got this reservoir, this oil platform, this pipeline, really high-level granularity systems, which are then broken down into technical systems to say I have a separation train, followed by a compression train, followed by another separation train, followed by a compression train. And then you break it down further into component systems, which saying that separation train has a gas liquid separator and a pumping system, and then so on building down, which you can then realize by a product model of artifacts, which can then be related to an installed plant model. Now, DXB Plus for process engineering covers this functional model. DEXB and THFOS and 15926 Part 2, and my understanding of most of Part 11, covers the product and installed aspect of a model during design. So this is unfortunately rather unreadable, but what we see is that DEXB Plus has defined a set of classes and a UML structure for that is able to represent a standard PFD in a good way, and there's a rather clear relationship between what you have in the PFD and what you have in the design, and you can use these objects also as placeholders for design information and requirements in your engineering database. So DEXB Plus has all been about integrating existing standards. We started with SysML, we've brought in AutoCAPE, we look at the MPro lifecycle, we can use 1596 activities to type and characterize the blocks. We use the system engineering approach for aspects, technical systems and component systems. And we've validated this with the NOACA process design for this oil and gas platform. And so what we have is a hierarchy of process steps where you characterize your process steps by verbs, not things. And there's a library of process steps which cover what we believe is about 95% of the chemical engineering discipline. Now, of course, we need to advance it and move it into different domains, but what we have now is something that I believe is a pretty good starting point for building chemical process models. And it can be also implemented using existing modeling and data representation languages. One of the questions we have about DEXB Plus is, okay, we have a data model. How do we then realize it? Well, we can realize it as RDFS. We can also realize it as automation ML, if you wish. And what we did as a prototyping work is that it actually fits very nicely into automation ML, and it actually builds on some of the classes you have in automation ML. So what we're hoping we can do here is actually use this standard to be a little bit of an integrating standard between other standards. And as an example, we took a very non-trivial but public example to demonstrate how it could be used. And there's a Tennessee Eastman version in DEXB Plus, but there's also a paper that I'd like to share the links with, which describes a little bit earlier stage of a work where we were using a SysML representation of a Tennessee Eastman process to see how these approaches to system modeling work. And so there's the resources for the case study. As a summary, what I'd like to say is that this, I believe, is something that is very complementary to the current workflows, which are very, very related to, I have an artifact that I need to do functional design for that artifact and then manage it through that life cycle. DEXB Plus provides a frame for defining your process and safety functional requirements at a level that is one level of abstraction up from the actual equipment, and it provides, I believe, greater accuracy and easier implementation when you try to do process safety and control analysis when you're in operation. So thanks for your attention.
Thanks a lot, David. Do we have any questions to David? Very interesting presentation. No questions at this moment. I was wondering about this. DXP Plus and this process flow diagrams and process block diagrams, is there a kind of time schedule when they will be published?
They have been submitted to, I sent off the draft standard and supporting data files to DXP last week, and they should be up anytime soon.
Okay.
So it will be coming hopefully very soon, and then that will be open to review.
Okay. What are the plans to get that integrated into engineering tools, or is there any plans for that so far?
The idea at the moment is to integrate it into the DXP data model. That is actually pretty straightforward in that everything that has been done in DXP Plus sits in another package called process that can just plug into the DXP data model. There's questions now related to, well, what serialization do you want to have for this model? We see also that there's opportunities to align DXP Plus with initiatives around simulation, because there's Cape Open has had work around trying to find open interface to shuffle data in and out of process simulators. My impression of what happens in industry at the moment is that most data transfer in and out of process simulators is done by very, very large, very, very fragile Excel spreadsheets. Now, DXP Plus provides us with a framework where you can actually build I believe, reasonably sustainable API for data extraction from simulators.
Okay, very good. Okay. Any questions? Any other questions to David? If not, we have planned to have a 10 minutes break at this moment, and maybe I can put it the clock visible here. Text is in Finnish, but numbers are universal. So let's take this 10 minutes break at this moment, and we can come back a little bit earlier than this timer is ending. Okay. Okay. We are now about time to start the last period of our webinar. Is Matti and Gerardo on the line?
Yes, I'm
Yes.
here.
Hello, yes, I'm also
Okay, maybe you can already open your screen and
sure,
share the presentation.
sure thing.
I guess we could start directly. Go ahead.
Okay, cool. Hello, everyone. It's great to be here as part of this presenting in this THTH Spring webinar. Thank you to THTH for this presentation. Today, we're going to be presenting together with Matti Huhtinen from AFRY the result of some of this collaboration that we have been having for the last months, related to, as the title says, making all PNIDs intelligent through the XP. So just some presentations. Good that we have the pictures since the cameras are not working now. So I am Gerardo Santillan. I am a senior specialist here at Semantum. I have been with Semantum since 2008. I'm just doing different things related to modeling, simulation, and also engineering automation, which is the topic of this presentation. Matti, please.
Hello, my name is Matti Huhtinen and I'm application key user for process engineering tools in AFRY and started in 2021. So over 2 years at AFRY and key user for process engineering tools. Thank you.
Thank you, Matti. Yeah, so maybe just to start with the agenda, how this will be. We already introduced each other, like Matti and I. We will just say some things about our companies. We will introduce a project, we will show the workflow, and then the idea of this presentation is that it's based on a demo. So we will demo the tools and the workflow that we are following to get these all diagrams into digital, into intelligent diagrams, and then some conclusions. To begin with some things about Semantum, many of you here know us. We are a software development company. We are in Espoo. Many of us have background from VTT, Technical Research Center of Finland. We are just a software development company, but we have different people with different skills in the company. We are software developers, we are automation engineers, and we have different focus areas. We have, as I was saying, we have a lot of modeling and simulation related offering, but we also, and especially today, we're going to be speaking about these engineering automation solutions for which we have been developing this model broker family of products that I will present later. But Matti, would you like to say some things about AFRY?
Yes, of course. So AFRY has established 2019 when OAP consultant Peiri made fusion, and after that there came a global engineering consultant company who will cover support customers of globalization and urbanization, digitalization, climate change and sustainability. And we have product industries, energy, infrastructure, and AFRY X in our company, and AFRY will focus sustainability solution and from 2019. And for globally, we have 90,000 employees and we speak more than 50 languages, and annual revenue is 2,000 billion euro and office is more than 40 countries, so very, very global company.
Thank you, Matti. Yes, so now right into that topic. So what are we doing here in this project, and in general, what is this workflow that we have for converting these diagrams into intelligent diagrams? So to begin with, to say that piping and instrumentation diagrams are really important for any process facility. I think that most of you in this meeting know what is a piping and instrumentation diagram, but in case you do not, you can see here an example. So as you can see here, all the structure and different information related to connections, and also, for example, the control system of the process plant is here represented in this drawing. So as you can imagine, is really important for different applications over the life cycle, starting from the design and later during the operation of any process facility. There is this issue that these piping and instrumentation diagrams are usually stored in formats, in CAD format sometimes, but sometimes not even like that. That make it difficult to extract information, and that also it's not really suitable for any kind of integration with other applications. So it is just a drawing with some lines and just some information there that is human readable. And then it is possible, yes, to convert these diagrams, but of course, converting many diagrams to machine readable formats is always costly, and many times it's prone to error because it's mostly done manually. So this is really an industry and a challenge that industry has in general. And digitizing these diagrams, making these diagrams machine readable would allow using this information available in the PNIDs to be used for many other applications that can increase productivity during the engineering, so during the plan design, but also during the operation. So this is also relevant not only for EPCs, but also for owner operators. So there are many applications for which this can be used. Maybe one of the most common applications is to bring these dumb diagrams, these drawings into modern CAD systems. So that is maybe the most important and more common application, but it's also possible, for example, to use the information to create simulation models, or also to populate engineering databases or other industrial information management systems. And also, for example, to create these data asset management systems. And also important to use this information later, for example, during the operation, when sometimes the process needs to be, either the process or the automation systems need to be re-engineered. So it is important to have this information in a machine readable format so that it can be reused for these cases. But Matti, would you like to elaborate on why this diagram digitization is important for AFRY?
Yes, of course. So for AFRY, we have many customers, stuff like UPM or Metsä, who have many diagrams with non-intelligent form. Of course, these plants have built 30 years ago. So of course, 30 years ago, there is no way to make intelligent PIDs. So AFRY have many customers who really have a lot of non-intelligent PNIDs, and this is important for AFRY because with these model broker tools and Autodesk DXP plugin, we can really convert these non-intelligent PNIDs to intelligent with the model broker tool. So this is very huge step with digital twin for existing plants. Of course, when we made new plants, then we, of course, if we don't have existing diagrams, then we make intelligent diagrams right away. But we have many projects. We have made old diagrams when we have a Perry have made old diagrams for the plant, and then we can reuse it and make it intelligent with the model broker at one time. So this is very, very impressive for API.
Great, Matti, thank you. So now to move forward straight now into the workflow. Maybe to begin with some background information about the tools. I think most of you in the audience know many of these, but okay, first of all, to begin with Model Broker. Model Broker is a tool that we have been developing in Semantum, and more specifically, this Model Broker for diagrams is a version of this Model Broker that can be used to digitize engineering drawings. In this presentation, we're going to be focusing on piping and instrumentation diagrams, but this tool is also able to digitize also control logic diagrams. And in a nutshell, what Model Broker is doing is creating DXP files from existing drawings in vector formats. It's also possible to create CSV tables, but for this presentation, we're going to be showing this DXP output from the existing diagrams. Then to introduce DXP is an interoperability standard to exchange information between different tools related to the piping and instrumentation diagrams. It is vendor independent, and it's also supported by major CAD software vendors, EPCs, equipment manufacturers and also research organizations. So yeah, it's an XML-based standard, as I will show later. And finally, to present the target tool in which these intelligent diagrams are being created, AFRY is using AutoCAD Plant 3D by Autodesk, and it is as the name says, is a tool to also create 3D models, but also the piping and instrumentation diagrams can be drawn in the same tool. So all these PNIDs are then imported. Once an XP is created with Model Broker, then they are created into and visualized in this Plant 3D user interface. We will have a demo on all this workflow, but just to be more specific and to maybe be redundant here, since I already explained most of this, what we are doing here is we are taking all diagrams that are available in vector format, and then we are configuring Model Broker so that different connections, different text, and also symbols are recognized. And then we create the XP XML, the XP file we exported from Model Broker. And then what we are doing is we are importing it into AutoCAD Plant 3D. AutoCAD Plant 3D has this XP Plant 3D plugin that it's kind of a wizard that can be configured so that you can map symbols that are available or different classes that are available on the XML of the XP, and then you can then import it into the corresponding symbol of Plant 3D. And finally, after all this configuration is done, then it is possible to have the intelligent diagram. Important to say that this intelligence comes from having this diagram that includes different components, also their attributes, and also different connectivity information. So it is a way more, it's a richer format than just the PDF or the DXF drawing from the diagram. This is the workflow. Yeah, and let's jump now right into the demo. So I will start now by showing this Model Broker part. This is Model Broker. This is the tool that we are using to digitize the diagrams. We first start by importing a source file. In this case, I will start importing DXF. This is a vector drawing. It's a PNID. We will now load it. It's a quite big diagram, but we will see how it is imported eventually. The tool is also supporting PDF, and also it's possible to import the WG. So this is the diagram. Let me change this to, for example, well, actually I will use the color so we can see how the diagram, this is a diagram that is had been drawn by AFRY. You can see here, well, actually this is better. But yeah, so this is a process PNID, quite common symbols that are found in other processes. So the idea of Model Broker is that we need to configure different symbols and then map them into the corresponding DXP class. So what I will do now is I always show this example of the valve because the valve is maybe the most common symbol available in these diagrams. But yeah, let's start with that. So I can all these symbols are built by something that we call primitives. So different graphical elements that are creating this symbol of a valve or pipeline or an arrow, etc. So what we have to do is to select the different components that are building this valve, these different primitives, and then we need to create a pattern. So as you can see here, this is the graphical representation of the valve. Let's call it just gate valve. Then we will select that. Well, we have different configuration options for this recognition. I will not go in detail because we don't have time, but what we can do now is like we can tell the tool that this graphical, this group of primitives that look like a valve, we need to map them into the corresponding DXP class that it's a gate valve. I think that's enough now. So I can close this. I need to select the diagram that I want to start translating. And I can see that I recognized 9 of these valves in the drawing. So, but then we were not able to recognize this. This is just because of different configuration options that I have here. I was not allowing the tool to have any flip or rotation, but I will tell the tool now that it is fine, that all the flips and rotations can also be recognized as valves. And as you can see here, all the gate valves are now recognized in this tool. What we are doing in this tool to manage connectivity, we have these terminals. So what I have to do now is to add different terminals to these valves. I will, for example, find this valve. Well, actually, I can do it here. And I will just say that I want to add terminals to this symbol. So I select these points, I add terminals, and then I just say that I want to move these terminals to the center of the symbol so that, as you know, the valve is always connected through this part of the drawing. I could also just say that the entire line is a terminal, but just to make it cleaner, I'm just saying that these are the terminals. I can update this. I will select from already that I want a DXP file as a target format. I can start configuring this. And of course, now we don't have anything because we haven't configured pipelines. But what I can do is start configuring some pipelines so that we see connectivity here. So that is the same idea. I can just select the primitive that is a pipeline. I can just create a new pattern. I can say that this is a pipeline. And then I give target in DXP as a pipeline. I can give this. These are the different connectivity options that I have. So I will give pipeline network segment. Then I also need to tell that tool that I want to create branches and split lines from this. And I want to use a pipe T as a target for those branches that I am creating. And I can update. As you will see, the only thing that I am able to recognize now is that line or the lines that are very similar and not the other pipelines. What I need to do now is just because I have many different configuration options to deal with this, I can use different constraints so that I can actually recognize the entire pipeline. So I will just tell the tool that I am not interested in any kind of control point that it is defining this specific line, but I am just interested in having a line there, and I will use different constraints so that I can recognize this pipeline. First of all, I don't want to be closed. Then I want these lines to be orthogonal so that the connections are always perpendicular. And another thing that I am using here, since I have a DXF file, I can just click and say that the layer in which these pipelines are, it's called basic. So I can just basically copy paste here and then say that I want all the layers, all the lines in that layer to be recognized as pipelines. And then I also need to include it in the route. And I think I can now translate this and see how different connectivity. Yeah, indeed. So first of all, I have here that I have recognized a valve. This is a gate valve. And then I can also see that it has different connections to a pipeline, to two different pipeline segments. So from that configuration of the pipelines, I can show, for example, all the different parts that were recognized as pipelines. These other pipelines are not recognized because, as you can see here, they are in different layers. So what I can do is just, well, I can actually do it very fast. I think it takes 10 seconds. So I will add here the tool. I will add another constraint to the tool so that I take my keyword is now. Yeah, that's the demo effect now working on my keyword. But yeah, maybe I don't do it now because it will take some time for me to configure the keyword. But I can add an OR symbol there and all the pipelines would be also configured. But what I can show now is we already configured this diagram, of course, and we can show how this configuration is recognizing everything on this diagram. So I can just open this configuration. I will replace what I have created just to not create any conflict. Here you can see that we have configured all the symbols for this diagram, and now I can run the translation. And what we can see here is, for example, let's start by showing all the different things that are recognized. Valves, pipelines, arrows. If I go, for example, to some equipment here, let's see where this is found. This is found here. Well, that's just a symbol definition. For OPCs, we have, this is an OPC that has been found. We also have information of the connectivity, for example, here, how different components are connected, etc. So in general, this tool is able to recognize text, also symbols, and also connections that we have in the PNIB, and then export the results either as a CSV, comma separated value table that can be opened in Excel, for example, and it is like enough for many applications, but then also the XP, that is the machine readable XML following this Proteus schema. And then I can show basically how it looks. This is the XML that we can create from that diagram that I was showing. This is machine readable, it's an XML, this is the XP file, but then we also have this visualization tool where we can actually check how this DXP file is visualized. This is only a visualization tool. This is not any CAD software. We cannot add or edit anything here, but it is useful for us. We use it as an internal tool in Semantum just to verify that the result of this XML is good. So for example, we can see here this pipeline that I'm selecting. We can go to the piping network segment, and we can see that we have a tag name here that comes from this text that we recognized and configure as a tag name here. And very fast, I can show here this connectivity view where we see the blue lines are process components connected, red lines are signals from instrumentation, and then green lines are equipment connections to their nozzles. And this is how this is coming from the XML that we configure in Model Broker. But please, Matti, so now you can please show us what is the rest of this workflow on AutoCAD Plant 3D.
Of course, of course. So I will share my screen first. Please say when you see it.
We can see it now.
Very good, very good. So I will show you very shortly what happened when we use this model broker tool and we get this XML file, and we have THTH plugin which made by Autodesk and with this model broker we get this XML file, and with the THTH plugin we import this XML file to Plant 3D. And now here I have Plant 3D 2023 open, and I have my Plant 3D demonstration project open on one drawing in the Plant 3D project. And as we see here, we have data manager, and as you see, this is totally empty. Plant 3D database is totally empty. There is nothing. And also my DBG is totally empty, so there is nothing. Okay, so now when I have the THTH plugin, there is own command THTH import. I use this, and then I get XML file which based to my AP Plant 3D configuration and also model broker. And then I take this same proper one group XML with made by model broker, and then I click OK. So I need setting XML, mapping XML, and this drawing XML. I need 3 XMLs over here, and when I use this import tool, then I set XML, and now it depends how big drawing we have. Of course, if we have very large drawing, then this import takes time. And now this is quite little drawing, I say. So now you see this Plant 3D THTH plugin read the XML all the time, and now all the components appear one by one to my drawings. And now these symbols, this drawing is intelligent, and now THTH plugin will read XML all the time. Now there come all lines, all tanks, all valves, all instruments come here. And of course, when we use this model broker, we still need to understand how Plant3D works. So we need to map all symbols with this mapping XML. We map all symbols to correct Plant3D class. So if we use THTH standard, so in THTH standard we have A2101 is for general valve symbol. We have 0101 is for tank, etc. So with this model broker, we map all components to correct Plant3D class. And then we can choose if we have it. Of course, that depends also if we have a non-intelligent diagram where we have no information, example pipeline numbers or tank equipment IDs, everything like that, then it's very impossible to use model broker tool if we don't have informative, non-intelligent PNIDs. But now we have all line numbers here, we have tank IDs here, we have loop function and loop number here. So everything we can put to Plant3D database. And now when this import successful, I can take a look that, okay, we have a line here. I take properties open, and in here we have S-line symbol. So this S-line symbol is intelligent line. So this line includes some attribute, some metadata, whatever you want to call it. And now we can choose where we get this information. We can get this line information for whatever we want in Plant3D, or we can make it separately. That comes from model broker and Plant3D setup, that we can choose what information we lead whenever we want in Plant3D database. And in here, if we take a look data manager, that was empty. So now we have everything here in place. We have tanks here, we have filters, we have pumps. In this drawing, we have 11 pumps. We have 133 lines, and of course we have more segments. So we have 154 segments, but everything is in Plant3D database. And now I can continue that. I can edit this diagram, and I can continue, or I can use it just like this. So I take a look that we have valve here. So there is a valve. We have tanks. Yes, there is a tank classes, and we have a pump. Yes, this is the pump classes, and then we have a instrument classes. So that is what I want to show you.
Thank you, Matti.
Thank you.
Thank you, Matti. I just share my screen was last time to show some conclusions, but here. Yeah, so thank you, Matti, once more. The idea, as you saw, was to create intelligent diagrams through this TXP. And as we have shown, then it's possible that, it's quite great. With this, we have, in our experience with Model Broker, we have come up with this number that it can reduce up to a third of the time that is needed to digitize these diagrams that otherwise would be done manually. So this Model Broker really reduces the amount that is needed for this diagram digitization. And the XP is key for this. The XP is, of course, needed. It's important and it's great for creating intelligent diagrams, but we have also seen many other applications that are possible with the XP. And this whole Model Broker idea is using the XP as a source for many other applications. And yes, Matti, maybe some things about how important is this for A3. Would you like to add something already there? What is on the text?
Well, no, this is in this last column, I I want to tell that because we Autodesk don't have developed this kind of tool that we have smart intelligent diagrams right away. So that's why we have a model broker. Before model broker, if we want to make intelligent diagrams from non-intelligent diagrams, we mainly need to redraw it. So that removes a lot of manual work when we use this model broker.
Right. Thank you, Matti. But I think this is it for our presentation. So any questions?
Thanks a lot. Any questions? Brief questions can be taken now. I have very detailed, very short questions regarding those terminals you mentioned, and I was just wondering if that equals to those ports what David Cameron was mentioning. Maybe you can answer, or maybe David can answer. You are both experts in DEXP.
I think terminals is mostly just something that is exclusive for this model broker to recognize connectivity between different elements. But I don't know if that would be equivalent.
Yeah. The DEXP standard doesn't use the idea of ports.
Yeah.
Okay.
That's been introduced into DEXP Plus because the way you connect in DEXP is through having piping nodes and nozzles.
Okay.
Yeah, I think the origin is in the steady state or this kind of a simulation programs which actually have used for tens of years these ports and terminals. They have streams and ports and unit operations. So that is the origin, kind of like. And because also at Semantum we have a lot of background in simulators, so we tend to use these terminals in the unit processes as well, because the simulators use them. But it is also a useful concept here in the model broker.
It's very
very okay. So I guess we need to take the next presentation. Miikka Tammi from AFRY is talking about model-based reliability analysis. Are you ready, Miikka?
Yes, I am.
Okay, very good. You can share your screen.
Yes, just a second. Can you see it now?
Yes, we can.
Great. So my name is Miikka Tammi. I'm a senior reliability expert, and I have worked at AFRY almost 3 years now. I received my Master of Science in Information Technology from Tampere University of Technology 2004. And since graduation, I have worked among reliability and risk management issues almost 20 years now. I have 5 years of experience in RAM method development and 15 years of experience in risk and reliability analysis work. And today I will focus on model-based reliability analysis. This is a large topic, and somehow it continues the story that Jussi-Pekka Penttinen started last year in this webinar with the title Probabilistic Risk and Performance Assessment. And because Matti Huhtinen already introduced AFRY half an hour ago, so I think I will skip this part of my presentation and we can save some time. So let's dive into this topic. These next slides represent design for RAM and model-based reliability analysis. And regardless of the presentation title, I will probably use more acronym RAM than word reliability during this presentation. RAM is a bit wider concept and stands for reliability, availability, and maintainability. And majority of RAM-related decisions have a big effect on lifecycle costs of the system. The earlier RAM can be affected, the bigger the potential for lifecycle savings are. Often over 80% of lifecycle costs are accumulated during the system's operation phase, but the most important decisions affecting these costs are already been made in conception and design phase. Regardless of that, in critical system, there is also often need to develop reliability, availability, and maintenance operations during the operation phase. And this requires deep understanding of the system operational state and risks. And using model-based RAM analysis, it's possible to analyze system risks and get a better understanding where the improvement potential is. It's possible to execute RAM analysis in many ways, based on history data or based on expert knowledge, or combining those both. Using simple or complex analysis techniques and models is possible. Analysis scope, target, and available resources normally defines the appropriate way. And this presentation, model-based reliability and RAM analysis, is introduced in 5 parts. First, simple analysis models based on device hierarchy and history data. Then modeling of failure modes, causalities, and future estimates. Then scenario analysis, and then RAM modeling and analysis at design phase shortly, and also RAM modeling and analysis of complex systems shortly. The first one is also called history data audit, and the first 3 together creates the basis of our history-based scenario analysis approach. History data audit combines and visualize data from different data sources. For example, device hierarchy, event history, and production losses can be combined and analyzed. Various analysis perspectives turn the data into knowledge that supports decision making, and it helps to identify the threats and the opportunities related to the availability, reliability, and cost risks. The basic idea is to upload all the interesting data at the same time and create a data model that can be analyzed via audit tool, and failure and cost trends, criticalities, top listings can be created based on this interesting data type. This is very fast and effective way to do data analysis, and the simplest of these model-based analysis types. This slide reveals also the following analysis phases. Audit part gives answers to question what is happening, and next question is normally what does it mean in the long run. The history data is a good basis for future estimates if data quality and quantity is sufficient. And expert knowledge is normally used to complete the data and estimates. Then we can understand the current state risk status and the most critical functional locations, equipment, and events can be recognized. And naturally, the last question is what we can do to improve the situation, where should we invest? And the last page, scenario analysis, enables planning of improvement actions, maintenance optimization, and spare part policy. And expert knowledge is often needed to estimate the effects of these improvement actions. Normally, it can't be made based on history data only. Next slide actually presents a really simple history-based analysis example. This case is turbine machine in hydropower plant, and the example is related to actual use case, but cannot be presented with real case data, so the failure rates and costs have been significantly modified. This particular case has really low number of failures and comprehensive planned maintenance, which are characteristics of hydropower production. And based on the event history, there is only 8 events occurred to the turbine during the 7 years. And cumulative event trend is quite stable, and corrective and preventive cost factors, work, spare parts, and loss of production together are only a little over 160,000 euros during this 7 years period. The event history of this single turbine is so scarce, and the history as such cannot be converted directly into a prediction. So we need to make the estimation of the failure behavior of components of this turbine shaft assembly based on failure history of other similar turbines and expert estimates. And we can use different kind of failure distributions based on the data source what we are using. This current slide is using mean, max distributions. And the failures in this case are not entirely random or unpredicted. And the failure distribution is shown in the screen. It is more straightforward to estimate the costs of failures and maintenance directly based on history data. Since no changes have been made, we can assume that the costs of these events are quite similar as before. Of course, corrective and preventive maintenance can be handled together or separately. And events are random when we are simulating the current state risk status. And then we can make a new simulation which reveals the current level of turbine cost risks. The mean value of total risk is about 128,000 euros, but the variance is cost risk is really high in this example. Most of the risk is related to the loss of production, and we can see from this risk distribution, that there is about 50% probability that the cost risk is only a few thousand euros during the next 7 years period, and about 40% probability that the cost risk is near 200,000 euros, and there is near 10% probability that the cost risk is over and much over 2,000 euros. And the last step of this simple demo is improvement action planning, and in this case, by monitoring the displacement of the shaft, many failures of the shaft assembly could be detected early enough so that unexpected failure and the consequence loss of production cannot occur. In this example, it was estimated that the new condition monitoring method will detect in advance about 75% of the defects of the turbine shafts. And so it's quite simple to do the change to the analysis model, for example, by using probability gate like here. And new simulation reveals the turbine cost risk level after the condition monitoring, and failure rate is still the same, but the cost risks are changed. And after this improvement, the simulated mean cost risk is about 64,000 euros, and the cost risk is about 64,000 euros less than before for this 7 years period. And in this case, the investment cost of this condition monitoring is 8,000 euros. So that means that the return of an investment time is less than 1 year. So really simple example of how we can proceed from history data and add some expert knowledge and head to improvement actions and get some smaller risk status. So history data is a great basis for RAM analysis. Whenever it is available in sufficient quantity and sufficient quality, but different type of approach is needed when enough history data is not available. And typically, RAM modeling and analysis at design phase is done based on design documents, including piping and instrumentation diagrams, expert knowledge, and generic failure databases. And there are a lot of advantages of design for RAM, of course. Possibility to significantly improve system availability and reliability. It enables moving from minimizing effects of process qualities during operation phase to preventing them already at concept phase. Also it provides an estimate for expected system availability and reliability. These days, customers are starting to demand throughout RAM reports instead of only a value. Also, we can calculate how different improvement actions affect system availability. Also, we can verify design plan from maintenance point of view. System designed to be reliable does not always take into account maintainability factors, and that would be really important issue at cost risk point of view. It helps understanding and acknowledging the remaining biggest risk factors. It can be seen what kind of availability and reliability related risks will remain and where it comes from. And finally, small work efforts have potential to make huge savings during life cycle, because we are in the design phase only. For example, a few hundred hours spent on dependability design, RAM design, can lead into tens of millions of savings in life cycle costs sometimes. The last part of this reliability modeling and analysis presentation is modeling and analysis of complex systems. And sophisticated method for RAM modeling enables, for example, modeling of process flows and complex failure logic, capacity restrictions, reduced production, redundancies, buffers, and usage profile. In addition, all types of events and cost risks can be analyzed. This kind of modeling can be done based on design documents, expert knowledge, and generic failure databases. And of course, it takes more time than history-based data analysis, but also it offers more versatile understanding of studied system and enables versatile action planning and continuous RAM development. Normally, we separate this kind of modeling and analysis in 3 phases. First is creating the system failure model. Second one is definition of critical equipment, and the third one is development of an action plan. So for first, system failure model describes cause-consequence relations of equipment failures and system level effects to operation and costs. Then defining and selecting of critical equipment is possible based on the system failure model and simulation results. And last, it's defining applicable and cost-effective actions for the critical equipment. For example, using reliability-centered maintenance methodology or something similar. Then there is a short list of advantages of continuous RAM development. There are same points than RAM design has, but also different aspects. Possibility to improve system availability and reliability. The improvement potential is highly dependent on system history and design. Understanding which factors lowers availability and reliability the most, and it's possible to occur a clear list of the most critical equipment of the system. Also finding out how different improvement actions can improve system availability. It allows estimating and comparing effects of different improvements. It allows focusing maintenance resources to the target and right targets. Also, it's possible to optimize system maintenance supportability. For example, delays coming from personal locations, spare part policy. And then we have better understanding on system risk factors and how to prepare for them. If no cost-effective actions can be found, the failure consequences should be lowered as much as possible by preparing for them beforehand. And as a summary, it might be good to mention again that it really is possible to execute model-based RAM analysis in many ways based on history and expert knowledge, or using simple or complex analysis techniques. And those all are important and have important role for RAM design and development. And always analysis scope, target, and the resources, which defines the appropriate way. I believe my time is up. Thank you for your attention. Any questions?
Thanks a lot, Mika. Any questions to Mika at this moment? No questions. This sounds really useful tool or concept. Can you consider this as a tool, or is this more like a concept or way to work? How do you?
It's both nowadays. 20 years ago, it was a method, and now it's also a tool which have been developed 20 years. And there's one tool for history data audit and one tool for a complex RAM modeling and analysis. And we are using those both daily basis in AFRY.
Okay, I guess setting up this kind of concept requires a lot of work and a lot of data. You are connecting data from different sources. Is there what kind of data is that data what is currently missing or difficult to receive for these purposes? Can you?
That's true, and it's a really normal situation that the history-based data is not, the quality of the data is not perfect, or the quantity of the data is not enough. So quite often we need to also add expert knowledge to this input data before we can do simulations. But the situation is getting better and better all the time. And one important missing piece normally is that we can get the event history quite detailed, but there is no link to production loss effects, and that's a big gap for utilizing this data for RAM analysis.
Okay. Okay, interesting. A lot of ideas came to my mind, but we are running out of time at this moment. But anyway, thanks a lot for your presentation. And last presentation is from Anders Hauser, Michael Meyer. Are you ready for your presentation, Michael?
I am. Hello, everybody.
Okay, very good. Share your screen and start your presentation.
I will. Just give me 1 second. Are you able to see my screen?
Yes.
Perfect. So, hello everybody. Thanks for inviting me to have this talk today. So I will talk about integrated engineering and how we can support your digitalization. It's a bit of an outlook, or look at how we work today with customers, EPCs and customers, and how we would like to work with customers in the future, what I'm working on. So just one second. Here we go. So quickly, who am I? My name is Michael Mayer. I'm working for Entris and Hauser Group Services in Switzerland. So Group Services is, let's say, a wrapper around all the Entris organizations worldwide. We supply tooling, processes, and so on to our sales centers. I'm working there as a program manager in the engineering department, taking care of the tooling. So tooling, I will later on explain what I mean with it in detail, but tooling used by our sales centers as well as customers, and also providing interfaces to our customers to integrate into their processes. My background is, so I have a diploma in computer science and a master of science in business computer science. Back then I came into touch with ontologies and classification of data. So this is why I really like this topic right now. Quick overview, what we have, how we work together with customers, what is integrated engineering. So basically, our customers are working on projects, engineering software. They have contractors like EPCs and, of course, business processes on their side. And we visualize this a bit with tiles. And so Entris and Hauser is a manufacturer of industrial measurement equipment. But we also, 1/3 roundabout of our turnover is solution and project business. So we're not just producing the equipment, but also handling projects and solutions with third-party equipment as a main instrumentation vendor for projects. Is there a question? Okay. So basically, integrated engineering is about the glue code of binding our customers with our tooling and the other way around, supplying data back. So a bit abstract, what are the benefits or the key benefits if you work with us with integrated engineering? So in terms of engineering software, we can supply an increase in data quality and consistency. So we are aiming for real electronic data exchange, not just exchanging PDF files, and also up-to-date product information, like single source concept. And also our platform, our engineering platform, is a collaboration environment. So it has roles and external access, so customers are able to access it as well as our internal people, and it's about working together on a project, exchanging stuff, and providing input over time and being more specific over time in order to provide a consistent offering and project offering. In terms of your projects, what's our aim with our integrated engineering? We want to have faster turnaround cycles instead of people calling and checking ambiguities. We want to be faster, import data in our platform as well as export it in a digital native way. Your benefit is also you can standardize instrumentation, like not order very specific stuff for a certain issue, but also being able to group it. And we also have the capabilities to detect if there's equipment that could be covered by a standard for your company or end customer. Also, the benefit is then reduced stock and spare parts. Instead of having 500 different instruments, maybe it's reduced to 50, then it's easier to have stocks, have some spare parts on stock. And also structured processes. So we provide an API and so on in order to integrate our tooling into SAP systems, which our customers already use. How does data exchange look today? So basically, we have customers using engineering systems like Comos, Aveva, Hexagon, and many others. And usually the exchange of data takes place using Excel files, many different Excel, let's say, formats. The data is not really standardized. So in the background, we're pretty much masters at reading in different Excel sheets. A lot of effort has gone into that. Even we trained some machine learning models in order to automatically detect what the columns mean, if we can automatically map it, because a lot of time is lost in projects with mapping Excel files that might even change throughout the project or inconsistent. Yes, we can handle it, but on the other way, it reduces the turnaround time, as I said before. Our aim is to have fast turnaround cycles so that you immediately get an offer from us. What does our engineering platform do with that data? So basically, this collaborative platform, we use it to do a device selection. So what's the proper instrumentation for your issue that you want to solve in your process? The sizing. So we're always interested on how much throughput do you expect, what line size is expected to be used, and so on. Also a configuration like, let's say, communication protocols will use hard, Profibus, foundation, field bus, and so on. This platform is also used to do the pricing and really interesting data enrichment. So the more data we get in terms of line size, what kind of material do you want to measure? Is it corrosive and so on? We can already supply more data back about the specific device to be used. So mostly, I will also show that right now, we start off with a little set of input and are still expected to provide a rough estimate for projects. Over time, this gets more specific and we enrich our responses, or we are able to enrich these responses with data. Also, a big part in there is, of course, documents and drawings, 2D drawings, 3D drawings of our devices that we have CAD drawings that are useful for engineers for planning. So how do we imagine the future to be? So we would like to have some more interfaces to engineering systems, not like export Excel files that we receive via email, but a more API-driven style of this. Yes, there will still be customers using Excel, which is perfectly fine, but our thinking is to have more in-depth integration. And our aim is not just to set up an entries and houses standard. This will not work, but we strongly believe in using standards. So of course there are different standards for data exchange via API or whatsoever, like DEXB, different IEC approaches for classification and so on. Also CFOS, of course, ISO 15926, E-class, and IDTA and the asset administration shell. So this is stuff I'm currently looking into. I'm pretty sure that there will not be a single standard as we cover many industries with our equipment, but I would really like to see this a bit more condensed. And in the past, so I've talked to colleagues that have tried to integrate customers with different standards the past 20 years. There was NE 100, and different other things, and it never really took off. And they're usually like, yes, it's a great idea, but the details are really nasty. But yeah. As I also mentioned, so we currently do provide an API for customers, which is used by some customers, not as much as we would like it, or in a broad sense that we would like it to be used, but there are already customers who integrated our systems into their SAP system. So if they send out an order, it's directly transferred to our system, and we immediately send a response out automatically. For instance, how long will production take, and so on, when they can expect the material that will arrive. So long story short, it's about using standards. Which one? I don't know yet. It will not be just one, but several. But anyways, this is really interesting for us. Quick look into CFOS. So that's one of the things I'm part of the CFOS steering committee. CFOS is about project handover, capital facilities information handover, specification as it's called. And this looks really promising because the oil and gas industry noticed that it's not worth creating a standard just for the oil and gas industry, but they want to address several industries. They were already able to attract the nuclear industry, and others are already looking into it. So this is one of the standards, I believe, or really hope that they take off for the exchange of information. Yeah. So this is a bit more in depth, what I've just mentioned, traceability throughout the project phases. So basically, we usually start off with EPCs with a pre-FATE phase. So this means they provide us with a tag and a function, but much of the things that we need are unclear. What exactly is supposed to be measured, how much? And over time, we get more data. In the feed phase, process data. So we are already able to create a rough, as I've shown it here, a rough digital twin. So as a response, we think this flow meter might match your requirements roughly. Then we get more detailed engineering data. So we enrich with this data, certificate specifications to be checked. During the execution phase, the real device is built. So we are, of course, able then to provide documentation, device documentation, manufacturing information, and so on, calibration information when it's manufactured, and so on and so on. So we enrich the data here. So it's a cycle between the software and our engineering platform to exchange and enrich information. And this brings me to my last slide. So what can we provide today? It's a lot of data. So this slide is filled with information on purpose. It's more than you can probably read in this short time. But we have a lot of information which is already structured, like length, insertion depth of instrumentation, seal type materials, design temperature, maximum temperature, and so on. And flange size, ratings, pressure ratings. And I think it's really worth classifying this data according to a certain standard, because it's really useful for customers, EPCs, to automatically evaluate at least the main data. Does it fulfill the explosion protection that is needed? Is the flange size the correct one that we asked for, and so on? I'm convinced that this will not be completely 100% machines just doing the data exchange, but our engineers and your engineers on the other side can focus on discussing the important parts that are worth discussing, and not how to map Excel files. I think that can be automated over time. As I said, we provide a lot of data today, which is already available, like 2D drawings, 3D drawings, E-plan, electrical diagrams. We also have spec sheets, Excel spec sheets that are asked for, NORSOC, NE100, and so on, E-class documents that we can export. And also, as I said, it's about collaborating for us and not just having an internal platform. You can already access it via our homepage entrus.com. If you can create an account for free and have a look at this platform. So this brings me to the end of my presentation, and I would be happy to use a bit of time for discussion and your input. What do you think about this approach? Any questions?
Thanks a lot, Michael. Very interesting presentation. Is there now any questions or comments to Michael at this moment?
I have a question for the audience, actually. So
maybe this is a good way. Maybe you could ask, because we now it is time for this discussion, actually. So we could start from this point on.
So basically, for me, it's always interesting to see the other presentations, and they are using or summarizing data, as we've seen from one of the prior, from all of the presentations. They summarize the data and insert it into a database. And as I've not yet really seen, but nobody ever asked us for really structured data. Everybody pulls Excel sheet from us, even though we could provide more. So I'm really wondering, why has nobody asked from the project side ever for CFOS classified data yet? So to instrumentation manufacturers, we want to push that a bit.
That reminds me to my question. I was thinking that because you are in the CFOS steering committee, and to my understanding, you are the only one representing equipment suppliers. Is that correct?
Yes, so I'm part of the steering committee. As we said, we wanted to push the things a bit on the equipment manufacturer side. But there's also another equipment manufacturer who joined CFOS. It's Yokogawa, as far as I know.
Okay, very good. So
yes.
So you two are there, and my question here is that you have seen CFOS now, I guess, quite deeply. And you have understanding what kind of expectation those CFOS owner-operator members are putting on you or any other suppliers, and are they asking now digital from you, as you are a member in the board, or are they still talking more about this transfer file based data exchange?
So to be honest, in my opinion right now, so the exchange takes place of data between the EPC and the owner and operators. But the specification on how to exchange data between the equipment manufacturer and the EPC or owner and operator, it's not yet defined. So this is one point I'm looking at right now, to actually get a specification up and running, what the manufacturers have to do. So to push that a little.
This has been today's webinar main subject, as you noticed, that how to get that part improved, and that is an important part.
Yes.
Yeah, Jukka, you opened your camera. Maybe you have a question.
Oh yeah.
Well, at least I have a comment.
Okay.
Thank you everybody for your presentations, and I think it is very difficult to pose very detailed questions to any of you, because in my opinion we at Fortum have something about everything in place. And then anyway, the situation is that or the problem is how to combine these into a functioning approach, and this means that we may have something which is not in a certain area, something which is not as modern as you have done in the latest days or so. But and it, I suppose it means that each of us customer companies creates their own system or their own structure slightly in a different way. So we can't expect any heaven right in the beginning, or maybe not in the future either, in the long run. I have calculated that when we are thinking about how to unite the things by using things like RDSPP or E-class or different structures, processes, it may be that we need something like 11, 12 different keys in combining the different data together. But if and when we have these, then we could combine most everything from one end to another end. And it may sound quite horrible to do 11 keys for this, but because they are quite related to each other, it may not be too difficult. So just to mention this in a way that this is in practice what we have to do, one by one maybe. But anyway, thank you very much for these presentations. They in their own part give some more comprehensive understanding in this area.
Yeah, thanks for your comments. Important comments. I'm not sharing that deeply your pessimistic view that maybe we never can get this combined, because this is now the effort what we are starting, and what Jerker was starting to explain. We need to have a systematic approach and system engineering issues, as David explained, and we always need different standards, as everybody has explained, and we need that for interoperability. But the difficulty is that we are applying those standards in a different way in different companies, and that is one obstacle. And to my mind, the example what Jerker had in his presentation, the same standard, and they looked totally different. That is always a difficult issue. But one part of the work what is now embedded in this Arrowhead FPEVN is this transformation between standards, and we have several different standards, and it is enough if a company is committed to utilize standards in a systematic way. And I don't know in detail what would be the systematic way, but for instance, today's presentation, I paid attention to David Cameron's presentation. He was giving some background information about that, what kind of different aspects and different needs we are having, and for those we need to put these standards in a proper way, and then we need to find out how to make this transformation happen. That this is definitely important. Would you like to comment anything, David, about these issues, or those comments what Michael and Jukka was telling?
Yes, I think the when you get into things like E-class and the detailed standards for parameters and these sort of things, you're really very, very down at I want to buy a specific component or a specific thing, and that is incredibly important and incredibly detailed. But I think the challenge about a lot of our engineering information organization now is to try to put requirements at the right level so that you down at the point where you actually need all the specifications for a specific type of pump. Yes, it's stored down there, but one of the things I saw was that if you, for example, try to use COMOS for design, you get a situation where you've got a class in COMOS which defines, for example, a pump. And that class has a couple of hundred parameters. And what you do in conceptual design, or what I saw an engineering company doing in conceptual design, was to say, yeah, great, we have a pump class, and we only put in 4 or 5 parameters at that layer. Now, that's okay, but what you've got then is you've got in your database this sort of evolving single view of reality, which is hard to version. And that's one thing I liked a bit about these ideas of named graphs and being able to rigorously version your information. And what I would dream of it being better is that you can actually say at the early phase is that I have an object which has just this set of parameters that you need to define the functional behavior of the system at the level of accuracy that is attainable or necessary at layer. And then you can just get steady refinement so that you're not, as I said, losing all your design rationale down in the E-class details that you've been given by your procurement people.
Yes. Very interesting issues. Is there anybody else who would like to comment at this moment?
I have some comments concerning these EPC and their sub-vendors. Even that the owner's operator requires data in specific ways, it seems that EPCs are not eager to have that equal data from their subcontractors, so that is something on a contractual level to agree so that you get what you really need on owner's operator perspective. And that is one point when we are thinking about these handover specifications, so that how to enlarge and so that the requirements are touching also not only EPC or EPCM contractors, so that also their subcontractors. I also think the big advantage is, so we sometimes have customers asking, so if we ask them what data do you need, they are like, well, give us all the data you have. That's usually a bad sign because then they don't know what they really need. I think CFOS is stripping that down a bit. So let's say for instrumentation currently, just a few parameters like explosion protection and so on, but at least that's a set that you can use as a basis and extend if you need more, but not just asking for all data, which will at the end make no sense, most likely.
Yeah, I think that the relevant data is what is needed for maintenance purposes and such thing, and operational issues. Of course, there are some technical data, and then there are also the data what is related to the, let's say, processes. So process technical process data as well, so that you have to share it in different parts. Who is responsible to give that data so that you have all data in right place so that you can manage the plant.
Can I just comment a little bit on that also? What we find, I've been doing a little bit of work with an EPC, talking to their vendors, and the life cycle, which was shown in the presentation on part 11, is actually a little bit more complicated than that, because what we do is we take a functional requirements, and then that defines the functional requirements, for example, for the valve. But then you actually have a couple of exchanges of information. You then go out with those functional requirements. The vendor comes back with a set of things they can offer. That what they offer may not match your requirements. You may have to change your functional requirements. So you then have an iteration there. And then you go out and say, okay, this is what I want to procure. And then you get back what is actually then offered for the procurement, and then you get what's actually being delivered. And so you've got an iteration cycle and the need to keep track of about 4 or 5 different data sets in that process, all relating to the same things, but it complicates your data flow quite interestingly.
Yes, and there has to be also responsibilities to update the data according to the equipment data what is provided, and then there might be also need to recalculate the process values after that, because they might have some limitations or something like that, so that you have all data.
Yes, exactly.
In order, so that it's an iterative process on that sense, yes, but anyway, you have to have the final data so that you know where to start to maintain the plant.
Okay. Any other comments at this moment? I would like to raise one comment actually that was from Leo. But to this discussion, what was going on here, is anybody else willing to comment or say something? If not, maybe I will raise that question. This senior management support and vision, what was required, that was according to Leo and according to our discussions, what we have done in our community here. That is a very crucial question. Those top management people need to be convinced that the solutions are will be done well, and they are useful for this company, and that is a big challenge, because we are still missing the tools how to explain all these details. Do you have any cure for this at this moment? Maybe all suppliers and companies have their own own cures and help. But this is something what need to be settled somehow. And this iterative type of working that is also continuing after the delivery and on online phase as these, for instance, these reliability-centric issues can be done online. That is important issue, and it means that we need to somehow make these information exchange as a collaborative workflows and something what is going on all the time. This is big issue, and part of this how to say digital transformation what companies need to do internally, and what these communities should agree together, because without common agreement we cannot start any kind of collaborative actions. And this is something what need to be done. Are you sharing this understanding or comment? Michael, what would you like to say something about that?
Well, so I'm just thinking. So we're trying to push it, but I think you have to start off with little things. For instance, we get a lot of spec sheets in order to select instrumentation. And I have a colleague who traveled around the world to actually not, or ask customers to not provide single spec sheets, but whole Excel tables. They were really surprised because they put a lot of effort in to use their big Excel table with macros to create single spec sheets, which we on our side used to create one big Excel table. So he traveled there, discussed with them and showed them our system. And they were really surprised because on both sides we had to invest unnecessary effort to actually read in that data. So that's the small steps in digitalization. And I think if you make people aware of these facts continuously, that there's even more potential to read in data in a structured way, we can get better over time, but I don't expect this to fully run within the next half year, to be honest.
You are correct. In this project, in this Arrowhead FPN project, we are having 3 years time to find different solutions and different ways to handle these issues. But I'm also pretty sure that after that period, we haven't solved all the problems what relates to this issue. So this is step by step working. But I guess now we are running out of time. We should close our meeting. Do anybody have any final comment to say? If not, maybe we can then close this meeting. I would like to thank all the presenters. Somebody has already left, but I will send a separate thanks, and I hope that I will receive the presentation from all your presenter as soon as possible. I will share that material to everybody, also to those who have not joined this meeting afterwards. Thanks a lot and have a nice day.
Thank you, everybody.
Thank you, Arto.
Thank you.
All
Bye.
the best.
Thanks, everybody. Bye-bye.
Thanks. Bye-bye.
Bye.